Okay, oh, let's see here. Yes, okay, we're recording. So, okay, here's where we were last time. We were talking about trying to take ideas from single variable calculus concerning integrals and figure out how to do something kind of like that, right? How to sort of extend to a multivariable context. And so that we know how to find area under a graph of a function of one variable. So how about volume under the graph of a function of two variables? Right? Seems like a natural extension. And okay, cool. So we proceed. And the big idea was to, as I like to summarize extremely briefly, chop it up, add it up. Right? You take your whole problem that's hard, you slice it into little pieces, on which hopefully the question is easier. So that's one of the big themes that you're going to see in all of the stuff that we're going to be doing with integrals throughout the rest of this course, frankly, is chop it up, add it up. That's what an integral is. You take a question, you chop it into pieces, and argue that the whole is the sum of the parts. If, in fact, that's how the quantity that you're interested in actually behaves. We're going to hear much more about that as time goes on. The problem initially was that when we look at the resulting little problem, it was relatively hard compared to what we saw in single variable because what's the cross-sectional area? It's not garden variety, right? And then we realized, of course, so that well, it kind of is because it's the area under a curve. Specifically, even it's the area under a graph, so it itself is another single variable integral. And so our cross-sectional area, sure, it's not a garden variety, geometric figure from early high school geometry class, but it nevertheless is something we do know how to compute the cross-sectional area of. So, boom, iterated integrals are the result. And this is about the last idea we talked about. All we did after that was to go through an example. And there are a lot of details in this example. Right? It's a matter of going through and following through the algebra. But remember, the big highlight, other than just, compute this inside integral, and then when you're done, compute the outside integral, right? So other than that, what's going on here, the big curve to be on the lookout for is to make sure to remember what's a variable and what's a constant. That's a little bit tricky. But if you're careful with it, it's really no problem. But you have to be careful with it, right? So specifically for the purposes of this inside integral, x is the variable. You treat x like a variable because it is. But don't forget the outside variable is constant. So that means that any expression of that outside variable is constant. Treat it like a constant because it is, right? And as such, the antiderivative of that becomes that, not 1/3 y cubed. That would be nonsense. Okay. All right. So that's the tricky bit. And picking up from there, so we let's look back at what we did. We sliced, and then we sliced our slice. Right? We started off slicing, you might say, in the y direction, thus producing slices that look like this. Right? And then those slices, you might say, we sliced in the x direction, thus producing slices that look like that. So we slice, and then we slice our slice. And which order we go in, the fact that we did the y slices, oh gosh, I'm going to say first. I don't know, you shouldn't say that, right? But in our slicing process, we did do it first. That forces y, because it is the first part of our slicing process, I think I can at least say that, that puts it on the outside, and therefore dx on the inside. Okay, so big question, can you do it the other way? Could I take this volume here, and instead of slicing first in the y direction, could I instead slice first in the x direction? I would have slices of bread like that. Those would have cross-sectional areas, which I could compute by slicing that in the y direction. right? Giving me a bunch of y slices, kind of like that. And how does that work out? And what do you get? And is that okay? And various related questions. So I'm going to leave this as an exercise for y'all. I think it's a lovely exercise. All you're going to be doing is kind of copycatting what I've already done in great detail here, right? And here. But punchline, yeah, sure, totally fine. No problem. Go ahead. And the really good news is it turns out kind of exactly like you would expect. So here's what we saw initially with our y slicing on the outside. And when you argue in the other direction, you are going to find that you get this. So the analogy is quite strong. Notice that in both cases, the integrand is the same. Well, of course it is. It's the height. Why wouldn't it be, right? So that, anyway, worth noting, though, it is the same in that sense. Of course, we're going to have our differentials in the opposite order. dy was outside there with dx inside there. Now here we have dx on the outside and dy on the inside. So it switches the differentials, right? But also, and easy to lose track of, it also switches the bounds. C to D, being as those are values for y, and over here in this new formulation with y on the inside, C to D bounds now also go to the inside. So you got to keep this as really important. A lot of students get this wrong. When you switch your differentials, you have to also switch the bounds. After all, the bounds really do go with the differentials. So this, what I'm doing with my hands here, this would be silly, nonsense. That doesn't make any sense at all. That's garbage, right? Obviously, you should switch the bounds with the differentials. So make sure to think through all those details. Go through the slicing argument just like we did, and make sure that you see, not only that you get this as a result, but that you understand all the particulars of why you get this as a result. Really nice exercise. Okay. Now, there is an asterisk on this. It's an important little asterisk. This only works when the domain is a rectangle. Now, this seems like a silly observation to make at the moment, because that's the only question we've so much as entertained at this point is volume under a graph sitting over a rectangle. That's a very temporary state of affairs. Very soon, as in about, just a couple of minutes here, we're going to start talking about what happens when your domain is not a rectangle. And there's a couple of little tweaks to the deal there. But anyway, no big deal. But anyway, try to remember this idea that you can just switch the differentials and switch the bounds. That's a peculiarity that works only in the case that we've been looking at here now, namely where the domain is a rectangle. Okay, absolutely does not work for any other domain. Okay, now here's an awkwardness. It's tempting to look at what we have here and say, victory. We got it. We figured out how to do an integral on a two-dimensional domain. Because after all, aren't integrals, like single variable integrals, are area under the curve. Now we know how to do volume under the surface. It's kind of the same thing. Aren't we done? Very tempting. After all, if you think about it, every application that we did with single variable integrals, I say we, y'all have done in your past with single variable integrals, it's just kind of it's the same slicing process, and you can compute area under a curve, but you can also compute the mass distributed across an interval on the x-axis, right? So the metaphor typically is you have a metal rod where the alloy has different percentages that vary, so the mass per unit length varies across an interval, and you want to compute the total mass. And use the same integral that you did to compute the area under the curve. Yeah, cool. Seems like we ought to be able to do something analogous in this situation, but we can't. And this is just one of the bits of bad news in multivariable calculus. The analogy does not extend. And here's my argument. Now keep in mind, I emphasize an important point here. Y'all heard me say this a million times. It's not about the result. It's about the reasoning, right? It's going to turn out the reasoning is going to work. The result is going to work. But the reasoning is not okay. If I try to take this idea of an iterated integral and use this to make a valid argument to compute mass distributed across a rectangular sheet where density, again, is given, just like in the single variable, mass distributed across an interval. This time mass is distributed across area, so density is mass per unit area. Seems reasonable. If I argue that, hey, look, we computed the answer to the kind of the graph question, if you will. We computed right here. Hey, how about I just compute the answer to the mass question like so? Seems analogous. Why wouldn't this work? And let me show you why it doesn't work. Again, as reasoning, it fails. Let's look at the successful part. Looking at this expression that we know makes sense. Right in the inside here, the very first construction that we start computing, and we have what we know is basically height being multiplied by basically a length, and height times length is a known quantity. It's something called area. We know area. We understand area. We know how area behaves. We know that area has this feature called accumulation. Area, I can argue that the whole is the sum of the parts. And I know it does because I understand area. We have intuition for area. I can look at a picture and just see how area behaves. That's why I can make this thing that I have on the inside here. Okay, fine, no problem. Let's try to copycat that now down here. Let's look at this inside integral, keeping in mind that we have our density, which is mass per unit area. Don't forget, right? Mass per unit area. And looking at this inside integral, apparently the first thing I'm doing is multiplying it by length, right? Just like previously. And now I ask, what is this thing? What is mass per unit area times length? I don't know. That's not a thing. The purpose of mass per unit area is to multiply by areas, which I am not doing. So I don't know what this is. I don't really know how it behaves. If I don't have a good intuitive understanding for even what this thing is, how can I assert persuasively that this is an accumulating quantity and that I can, in fact, argue that the whole is the sum of the parts? I don't think you can make that argument because this is a quantity that we have no previous experience with. So it just doesn't work. I'm sorry. It'd be nice if it did, but this inside integral that we wrote down, claiming that has something to do with mass, I don't even know what that is. So dead in the water, that argument does not make sense. And you can't do it. Okay, so that's something we're going to have to fix. This is one of the big reasons why I like to tell students, as you heard me say last time, that look, this idea of an iterated integral, it has its purposes and it's going to be convenient later, but please do not hang your hat on this concept. This is not something that is fundamentally going to work and fundamentally going to give us, in general, what we need. It's just not. Okay, yes?
Isn't the second integral, wouldn't that represent like mass over height or something? Because if the area is like the length times the height, you could like cancel the lengths.
Yeah. I mean, you could try to make such an argument, but then I'm going to have some questions like, oh, okay, so it's mass per unit, like width or whatever you want to call it. Okay, what is that? How does that work? I still don't know how that works. Yeah. You know what I mean? So I mean, yeah, and I emphasize also you can go through and make sense out of it, but it's a bunch of effort, and you've got to kind of reinvent the wheel. And then what you have is a concept that allows you to make sense of an iterated integral for one single application. And then the next time you want to compute something with an iterated integral, you got to go through and reinvent the wheel again. So yeah, no, it's a reasonable question, but it's just it's at best a very inefficient strategy. Yeah. Okay. Okay, so I want to go back real quick and remind you of single variable calculus. I know y'all know single variable calculus, so that's not our purpose here. But specifically, there's a detail that I want to emphasize, and that's the definition of what is an integral. And very importantly, what an integral is a Riemann sum. So this is a commonly misunderstood thing. A lot of people think that an integral is the area under the curve. A lot of people think that well, look, I mean, this whole business about a Riemann sum is some sort of an outdated, that's what they did before they knew the fundamental theorem of calculus. And my God, who would ever compute with a Riemann sum? Y'all were probably forced, as I was when I was in high school, to compute at least one integral with a Riemann sum. I thought, why would I do this? I read ahead. I know there's this awesome theorem out there that will actually compute integrals for me. Why am I doing it the old-fashioned way? Right? And first of all, historically, it's completely inaccurate. Riemann wasn't even alive when integrals came out. Right? So historically, that is just not what it is. The point here is that it's not Riemann sums are the outdated method that was replaced by the fundamental theorem. Riemann sums were an attempt, a very successful attempt, to take ideas of computing area under a curve and allow it to be applicable in other situations. So one of the great misunderstandings from high school calculus classes is this is not something that you should ignore. No, this is what allows calculus to apply. This isn't it's partly for mathematicians doing, ivory tower formalities. Yeah, there's an element of that. But this is what makes calculus make sense to a real-world scenario. So here's my little diagram to try to represent this. Let's take Riemann sums out of the little diagram here. No Riemann sums. All right, let's suppose that I try to define an integral to just be area under a curve and claim that the fundamental theorem of calculus is a question mark again. That the fundamental theorem of calculus is something that computes areas only. And let's try to use this little diagram of ideas to help us understand how to compute mass distributed across an interval. So, all right, fine. Question comes to us. We want to compute mass distributed across an interval. Here's our interval. It's one-dimensional. Nobody said graph. If you say, but I like graphs, okay, well that's your thing. But the question that comes to us is mass is distributed across an interval. It's an intrinsically one-dimensional question. And if you then try to argue that we're going to find the answer to a one-dimensional question with a fundamentally two-dimensional concept, I think you're making stuff up. I don't see any immediate connection there. Why should mass be related to area of anything? By itself, again, not about results, but as an argument, I don't think that holds water. Right? It just doesn't. So, sure, I mean, I suppose if all you care about is computing area under a curve, then yeah, I guess you could say that that's going to be your definition of an integral. But game over. End of story. No applications. Right? I mean, this is a disturbing development, disturbing realization. So this is why we don't define integrals that way. This is why we define integrals to be Riemann sums. Very importantly, integrals are Riemann sums because while I don't know how mass relates to area, I can absolutely rewrite mass as a Riemann sum. I can absolutely say, look, the whole is the sum of the parts. That's how mass works. Of course it does. I know mass. You know mass. You've had Play-Doh and cut it in half and had 2 pieces of Play-Doh, and the whole is the sum of the parts. Of course it is. Right? And so this, if I can rewrite mass as a Riemann sum, and if I understand integrals to be Riemann sums in the fundamental theorem of calculus, then effectively, morally, is a tool for computing Riemann sums, now we're in business. Now we can connect to lots of applications, right? I can compute populations as long, wrong color. I can compute populations as long as I can chop them into little pieces and make a Riemann sum. I can compute the amount of work it takes to perform a task if I can chop it into little pieces. Argue that the whole is the sum of the parts, and various other applications. Because I can chop them into little pieces, the whole is the sum of the parts, and I emphasize it's got nothing to do with area. It really doesn't. At best, area is a visual aid that maybe, I guess you could say, helps us visualize what we're adding up, I suppose. But there's no getting around the fact that we really need Riemann sums, and area is a kind of a little pacifier for us to make us feel better about it. Okay, so very important to understand. And with this in mind, let's try to do something similar now with a rectangle. Now here's a picture of a one-dimensional Riemann sum, single variable calculus Riemann sum. We look at our domain being some sort of an interval on the x-axis. Notice, one-dimensional picture. I don't need to draw the graph. I'm not computing area, probably. I mean, maybe, but who cares? So as the questions come to me, it's just one-dimensional. And the domain, I can chop it up into little pieces and argue about how the whole is sum of the parts. And on each little piece, there's some integrand that I multiply by size because, quantity per unit size times size gives me quantities that I then add up over that entire summation. So we're just going to do something kind of analogous to that now. And it's a little bulkier. But it's fundamentally the same idea. I'm going to try to figure out not how to chop up a one-dimensional interval into pieces, right? I'm going to try to figure out how to chop a two-dimensional rectangle into little pieces. And how are we going to do that? And well, I'm going to slice like so. That worked out better than I expected. And then I'm going to slice it again. Like so. And now, reminder, question: what am I computing here? What's the quantity in question? Well, rhetorically, let's come back to the single variable case. What am I computing when I chop up this interval? I don't know. Doesn't matter. All it has to be is something where the whole is the sum of the parts, and where on each little piece, on each little subinterval, I need to argue that there's stuff per unit size that I can multiply by size. Anything that has that feature. Cool. So that's why we can use, again, Riemann sums, aka integrals. We can compute mass distributed on an interval, or the amount of work it takes to perform a task that I can think of as being on an interval, or population, or, think back to Calc 1 or 2 or wherever this happens, and all the various different applications. Doesn't matter what we're computing. We're just chopping up and arguing that accumulating quantities, where the whole is the sum of the parts, can be computed with this construction. Doesn't matter what accumulating quantity we're talking about. So likewise here, this is just the strategy for how to compute an accumulating quantity. Maybe I have mass distributed across this area, and I want to compute the total mass. Cool. Maybe I'm computing the volume sitting over this rectangle under the graph of some function. Well, maybe. Maybe I'm computing the population of Wyoming or Colorado. Could be, right? Lots of quantities that I can view as the whole being the sum of the parts, and I can write it down as a summation. So don't get lost in trying to think about what the quantity is here. It's not the point, right? This is just a question of how to make a whole is the sum of the parts argument. And the particulars are going to be that I'm going to take each little piece of... I wanted to be in highlighter mode here. I'm going to take each little piece of area that I have here. And on each little piece of area, I'm going to want to multiply that area times quantity per unit area. Right? Forget about everything else. Forget about all these formulas for the moment. On that little piece... mass per unit area times area will give me mass, which I then add up over the whole thing. Population per unit area, otherwise known as population density. Population per unit area times area will give me population. How many people live in this little rectangle? And then I add up over all the rectangles. It's just chop it up, add it up on a rectangle. And this is the expression that we get when we take the answers on each little piece, we add up over all of the pieces, and then, of course, we do have to take a limit as n goes to infinity, as we have to slice finer and finer, because each one of these has round-off errors, and that's the formalities. But for sufficiently nice functions, that resolves all the issues of round-off errors. Okay, pausing. How we doing? Everybody with me so far? A couple of details we do have to talk about. What's going on with what are these coordinates down here, and what are these coordinates over here? Well, look, I mean, as I slice in the x direction, right, as I do this, notice I'm also slicing up, let's see, that doesn't come off very well. I am also slicing up this interval. And if you slice up the interval from A to B, you get all the same equations that we had back here, slicing up an interval from A to B. Sure, yeah, right, fine, no problem. Okay, that's old news. And then analogously, as we slice horizontally here, like this, right, notice we are also slicing up this interval from C to D. And now that I guess technically a little bit different, but it's not that different. This is C instead of A. It's D instead of B. It's going up and down instead of sideways, whatever. And I can still talk about how big these little pieces are and call that delta Y. And I can still talk about how far I've gotten from my starting point C as I move up in increments of delta Y. And that gives me my various, little checkpoints there along the way on the y-axis. Totally analogous to slicing up the x-axis. This is the details and particulars. That's just all that is there is a way of making this actually precise. In practice, most of the time, you're not really going to be dealing with these at all. Now, I'm going to do the same thing that high school teachers did, and I am going to make you compute a couple of these, right? It's not because this is a computationally useful method most of the time. We are going to find the fundamental theorem is going to kick in and make life easy, absolutely, right? The purpose of making you write some of this down and make sense out of it and successfully compute one of these n equals 3, for example, Riemann sums, is just to make sure that you get a clear picture of what it is that this expression is actually doing. It's purely pedagogical, right? In practice, most of the time, we're going to compute it with smart techniques. And so now let's move on to that sort of stuff. So, okay. So we finally can make a definition. We have a new idea called a double integral. We're going to use this notation here. The definition of a double integral is that it's the Riemann sum that we just talked about on the previous page. Right, so all this is a name and notation, not a new construction. It is a Riemann sum. Very important thing to realize about double integrals. Don't think of, in the same way that I think it's wrong to think of a single variable integral as being area under a curve. Just really importantly, fundamentally not what an integral is. Likewise, a double integral. Please don't think volume under a graph. It's not what it is. That's a marginally useful, I guess every so often you need to know the volume under a graph, but not really that often, frankly. This is a shorthand notation to represent a Riemann sum, which is how we compute accumulating quantities. The whole is the sum of the parts, chop it up, add it up. Very importantly, this is what a double integral really is. Now, before I do a couple applications, I do want to comment on some things that the book does. The book does get a little bit more formal in how it writes down double integrals. There is an entire field of mathematics that is about how to make definitions like this more and more broad in their applications. What I've written down here does have a nasty little shortcoming. What I've written down here only makes sense if the function f is continuous, and that's pretty restrictive. And if I ever find myself with a function that's not continuous, I'm kind of out of luck in some sense. How to make sense out of questions in increasingly bad kinds of functions. It's not what we're here for. There is such a thing. There is, measure theory is kind of a thing, analysis, but it's not really what we're here for. So all this stuff that the book does using irregular partitions and arbitrary test points, that is a few steps down the road in making this more formal and more broad in its application, and therefore really better, yeah, sure, but mostly for kind of mathematician ivory tower purposes, and for our purposes, for engineering and physics purposes, it's not that important. So you are not responsible. You can ignore all that business about test points and irregular partitions. Okay, so let's do it. Here is a question. We have a graph. We are going to look at a rectangular sort of base down here in the domain. And we want to compute the volume. Right? How are we going to compute the volume sitting under that graph and over that rectangle? Now, you could say we already know how to find the answer to that question. We're going to now, though, answer the question using our brand new shiny tool. We're going to answer this with double integrals. And instead of thinking of this as a slice of bread that we're going to chop up, we're going to think of this as a bunch of French fries in a large package of fries. Right? Not slices of bread. These are now French fries. And here's the thing. Each little French fry, no problem. Each little French fry, I can argue very easily, the volume of that French fry is going to be the height, which of course is the value of the function, because we're looking at a graph, times the area of the base. Let's see here, the area of the base there, this little sub-rectangle down there, delta x, delta y. Right? The volume of French fry is an easy question. And then I just have to say, look, I'm adding up over all of the French fries. I'm going to do that for every single piece of this rectangle, and take a limit, let n go to infinity, so the round-off errors will go away. Again, that always is, for the kind of functions we're going to look at, that's always going to be fine. And what we have done now, we have taken the question of what's the entire volume of my entire, biggie French fries or whatever, right? And I have rewritten it as a whole of the sum of the parts, because the parts are easy. And, oh my God, check it out. Kind of a coincidence, it would almost seem. I have exactly the definition of a double integral. I have exactly, let's see if I can, here we go. I have exactly that Riemann sum expression, and therefore I have literally a double integral. Is that cool? All right. Okay, now, I do hear reasonable questions coming out of your, subliminally, right? Yeah, but we don't know how to compute this thing. At least with iterated integrals, I know how to compute iterated integrals. You compute the inside integral first, and then once you've done that, then you can compute the outside integral next. Ultimately, it's advantageous to have single variable integrals because we have a single variable fundamental theorem of calculus, and actually turning the crank and computing stuff, kind of a big deal. If you look now at what I'm so proudly presenting as a better way to compute volume under a graph, this isn't a single variable integral. We don't have a multivariable fundamental theorem of calculus yet. So how do I compute this? Valid, right? I can't. We don't know. We don't have that tool. Okay. But quick observation. I could think of this. I could think of this as that I wanted to compute volume, and that double integral was how I was going to do it. Or I could turn this around and say, hey, if you want to compute a double integral, volume is the way to do it, and we know how to compute volumes under graphs. You do that with iterated integrals. Okay, so that's this theorem right here. We previously argued that volume. Let me get the colors good. We had previously argued that volume could be computed with iterated integrals. We have now argued that that same volume can be computed with double integrals, and therefore it follows that you can compute double integrals with iterated integrals. And that's a slick little move right there that allows us to sort of, now we see daylight. You first write the question as a double integral, you rewrite that as an iterated integral, and this, take your pick, either one of these iterated integrals, compute with the fundamental theorem. All right, now there's a bunch of different ideas down on the page. It does get confusing, all the different kinds of objects that we're talking about, so I want to kind of summarize, again, step back, starting from the very beginning, what on earth have we done? We started off with this. Volume under a graph. We argued that the loaf of bread is the sum of the slices of bread, made iterated integrals that we know we can compute with the fundamental theorem. So this we did first. But then I was unhappy about the fact that I can't relate applications to that. Right? I can't argue that mass is volume. It doesn't make any sense. And I also observed that you can't immediately write mass as an iterated integral either, because the units, if nothing else, the units don't work out. So that doesn't make any sense either. So this is where we were before we started talking double integrals. All it was, this iterated integrals is only a tool for computing volume only. That's it. Very limited. Then we defined this thing called double integrals. I argued that you can compute volume with double integrals, and then I say, well, what I did just moments ago is that if that's equal to that, and if that's equal to that, then it follows that that can be computed with that. Okay, so we made that argument. So this is where our diagram stands at the moment. right. And with that noted, yeah, but I still want to do applications. How am I going to compute, for example, mass distributed across an area? I know I can't argue that it's an iterated integral. Doesn't make any sense. Units don't work out. I can't argue that it's volume. That's a non-starter. It isn't. Mass isn't volume. There's no reason to believe it should be. That doesn't make any sense at all. Here's why double integrals are so important. Double integrals are the foot in the door. I didn't want that in red. It is perfectly fine because mass is an accumulating quantity. That I can say mass, the whole of the mass, is the sum of the pieces of mass. And I can, no problem, no units issues, no nebulous hand waving that doesn't actually make any sense. Mass absolutely is the sum of the parts. And now we have a pathway for actually computing answers to questions. So there's a 3-step process with all this in mind. That is how we're going to compute answers to applications. Step 1, rewrite your application as a double integral. The whole is the sum of the parts. Any application, any accumulating quantity, anything where the whole really is the sum of the parts, you can chop it up, add it up. Step 2, make the argument that double integrals, aka Riemann sums, are iterated integrals. And step 3, compute your iterated integral with the fundamental theorem of calculus to get your answer. 3-step process. And it works great. Is everybody on board? All right, let's see an application. Here is a question that we failed at previously. Right? We want to compute the mass on a rectangular sheet. Let me go back to our first attempt where we tried to make sense out of this. We were just a non-starter. I can't even write down that mass is this iterated integral because the units don't work out. I don't know what that is. That's not a thing that makes sense. I don't know if it accumulates. It just doesn't work. Right? Iterated integrals crashes and burns. But the whole is absolutely the sum of the parts. No issue there. I can just fine and dandy argue that mass, the whole is the sum of the parts. On each piece, how much mass there is in each piece is mass per unit area times area. That's cool. That's what mass per unit area is for. Mass per unit area means multiply it by area, it'll give you mass. That's fine. Right? And then we recognize, hey, check it out. There's literally exactly a Riemann sum. That is literally the definition of a double integral. Okay, so that's our first step. Now those 3 steps having been discussed, that is our, let me get this onto the page here. That is our step 1, phase 1 in our calculation. Is everybody good? Okay. All right, step 2. I need to argue that double integrals can be computed with iterated integrals. Well, yeah, right, of course. Whoa, that was a technical glitch. What happened? Oh, okay, I don't know what happened there. Come on, it won't erase. Maybe that's an illusion. Yeah, that was an illusion. Okay, sorry. Step 1, write the application as a double integral. Step 2, argue that double integrals are iterated integrals. That's already a theorem. There's really kind of hardly anything to even be done there, but we do have to doff the cap to the relevant point that double integrals can be computed with iterated integrals. Write that down. And then step 3, crank it out, plug and chug, because we know how to do iterated integrals. You compute iterated integrals with the fundamental theorem of calculus. Off you go. Everybody good? So we are no longer dead in the water on an application like this. The point is, we were trying to solve this question with the wrong tool. Iterated integrals don't make any sense for that situation. double integrals do. Okay, so notice when you solve one of these problems, I do need to see all three of these steps. Keep in mind, this is not a class about answers, it's a class about reasoning. Very often, students think to themselves, well, yeah, but it's obvious, like if I were to do this, well, of course I meant double integral. Well, this is the material of the course, right? You can't assume that I will assume that you understand the material of the course, right? That's what tests are for the purpose of seeing if you understand the material of the course, right? So I do need to see all of the steps here. If you do this, you've missed a very important idea in the computational process, right? I do need to see all three steps. Please make sure that your work explicitly shows a double integral, and that you explicitly show the resulting iterated integral. And then, at that point, go crazy, off to the races. Use the fundamental theorem of calculus to plug and chug. Okay, make sure to give me all three steps. That is going to matter in grading. Okay, now what I've done here is expanded more than necessary. You don't have to write down all of this. This was mostly for sort of illustration purposes. I think it's, once you've been down this road enough times, you're going to be pretty comfortable, and I think this is pretty reasonable going straight to there. That's fine. No problem. But I do need to see that. Okay. All right. Last little quick thing, and then we'll get on to some other applications. So it's about notation. This argument that I gave you here resulted in a double integral. Right? And there are situations in which you really do have to kind of make... sometimes it takes a little bit of doing to develop your Riemann sum. Let me say it that way. And as you're doing that, it is a little clunky to have to write down stuff like this. So as you write down stuff like this, if you want to sort of abbreviate that as double integral, because that's what it's going to turn into. We're going to observe that our Riemann sum is a double integral eventually anyway. That's actually pretty reasonable. So I will write down, and in my distant past physics days, I've seen this kind of thing a lot. I think it's perfectly reasonable to write mass integral dm. This is just the recognition that mass is an accumulating quantity and the whole is the sum of the parts. Right there, sum of the parts. And if you want to use dm is density times dx dy, yeah, sure, absolutely. That's just a shorthand notation. Case could be made. It's maybe a little of an abuse, but that's fine. Everybody does it. It's all fine. No problem. So these kinds of notations, very convenient, very standard, very understood, all good. Okay, so last observation real quick is about just one more application, and the world's your oyster. Now that you have double integrals as a tool, let's compute the amount of work that it takes to build a 6-foot high wall that is 10 feet wide, where density, the weight of the materials per unit area on the wall is given by some function. And so if you have these heavy, let's say we're making this out of stone or something, right? Those things are heavy, and you can pick one up off the ground if it's sitting on the ground, and you can pick it up and put it into your wall and stuff, and I don't know, spackle or whatever I don't know how that works. But the picking up of it is, that's a lot of work as it turns out. And the first one's easy, but after you've done about 1,000 of them, it's a lot, right? Your back is going to be not happy. So it would be interesting to know how much work this actually takes. And notice how convenient the shorthand notation is here. For each little brick or stone or whatever, Work is force times distance. It's sitting here on the ground. I have to pick it up to that altitude. The amount of altitude raised is y. There's some differential amount of weight in that stone. Weight, of course, is a force. So this just says work is equal to force times distance. And let's see here. Weight is weight per unit area times area. And lo and behold, notice we have ourselves now that work is written as a double integral. And so this shorthand notation, using double integral notation and differentials as a shorthand, I mean, really, honest to God, this is a Riemann sum. That's a Riemann sum. I guess I could have written it as Riemann sum, but I knew I was going to write it as a double integral eventually. It's compact and convenient. You might as well go ahead and use the convenient notation anyway. So this little shortcut is totally fine. Everything else in this example is details that I'll let y'all read through for yourselves. Notice density is right there, right? Then we have a iterated integral and plug and chug, and there's how much work it takes. Okay, y'all have a great weekend. See you later. Have a good one. Let's see here.